So in the olden days when we did refractive index of things, we would use a Hodgson light box. It's a difficult and clunky piece of equipment that requires the lights in the room to be off, requires a power supply, often doesn't work, often won't focus, etc. So these days we use lasers, and lasers are incredibly accessible. $2 shop will quite often have just a laser pointer, which is perfectly adequate for the purpose. We've got a slightly fancier laser pointer, but not particularly, and we're going to measure the refractive index of a block of perspex. Now, refractive index, we know that the refractive index of empty space is 1.000. The refractive index of air is very close to that. So we're basically assuming the refractive index of the air in the room is 1.00. Refractive index of water is about 1.33. Refractive index of perspex, we're going to calculate, so, but I happen to know the answer. So we can figure that out later and see whether we get close to at least the published refractive index of perspex, but of course this might not be pure perspex, this particular block. This is an experiment you could definitely do at home. You don't need a perfectly shaped perspex block with a handle on it. Really any transparent object will work, and you can find out the refractive index of your fish tank, for example, with a laser. If you try not to blind your fish is good. So in this case, I prepared a line earlier on the paper that is the line where the laser is hitting, and it's difficult to see the line, but once I get the object in the way, it's a lot clearer and easier to see. So I'm going to start with at right angles, and I hope you can see that the laser line is going right through the middle. I can move it a little bit so the handle's out of the way. The key thing here is the angle. So in Snell's law, we're working with the sine of the angle. So we'll measure the angles directly, and then we'll use that to calculate the refractive index. So in this case, what I'm going to do to take multiple measurements, because I've got a nice straight long laser line here, I'm going to, for the first measurement, just draw a line along the front of the perspex block and find the point where the laser beam comes through on the back, make a mark there, and join those with a line. Now what I've done there is make the incident angle 90 degrees. Sine of 90 is equal to 1, so it hasn't bent at all. It hasn't refracted and bent at an angle. It's gone straight through, so that's kind of a pointless reading. I could, if I wanted to, then predetermine the angles that I used. So I've got my protractor, I can decide what angle I want to slope it at, but it's probably actually really simple to just do a relatively random increasing series of angles as you go and take those measurements, measure the incident angle in degrees, the refracted angle, the angle of the refracted beam where it comes out of the perspex block, and then measure those two, and using Snell's law and the fact that we know the refractive index of the air, we can calculate the refractive index of the block. So let me do another example with a much more dramatic angle. So hopefully what you can see is that inside the block, the laser beam is going off by something like about 2 centimeters from that straight line. So I'll do the same trick. I will draw a line along the front of the perspex block. Oops, I moved it. Make sure it's back on my line. And then I'll turn the laser on and put a point where the laser dot comes out. I'll join that point with a line to the point where the block crossed. Now, the incident angle is going to be measurable here, and the refracted angle is going to be measurable here, and you'll be able to then calculate from those. If I take another measurement further along with a bigger angle, same deal along the front. Something has moved. There we go, we're better off now. So on a much bigger angle, again, make sure that I'm back on my line that I set. Make my dot, make my line to my dot, and I can measure. So as with most of these experiments, you'll want minimum 3, probably 5 or 7 data points to actually test and then average your result that you find. You've got your incident angle and you've got your refracted angle, and you can calculate from that the refractive index of the Perspex block. Okay, so basically for our refractive index data experiment, we shone a laser into a Perspex block. So it spent some time in air first and then into the Perspex block. Perspex is more optically dense than air. Quite often when we talk about Snell's law and refractive index, we talk about dense, but it doesn't mean in the usual sense mass dense, grams per cubic centimetre or kilograms per cubic metre. It means optically dense. And the two things are related but not exactly the same. So it's probably worth making that distinction for your students. So Perspex, we know, is more optically dense than air. So it means that the ray bent towards the normal. When it was refracted, the ray bent towards the normal. And you see that. So incident angle 28 degrees, refracted angle 19 degrees, all the way through to incident angle 60, refracted angle 35.5. So our situation was essentially that we had a slab of Perspex, rectangular. You have the normal line, the line at 90 degrees to the surface. We have the incident angle is the angle to the normal, theta I I'm going to call it, incident angle, and in this case, because it's a more dense medium, the refracted angle is going to be this angle in here, and I'll label it outside so I've got some space, theta R, the refracted angle. So that's basically all that we've got going on in this experiment, and what we did was measure the incident angle here using a protractor. We didn't measure it very precisely. We could have added an extra decimal place probably, but we'd be kind of judging by eye. So I ended up doing it relatively roughly, I guess, to actually work out. And what we did with the angle inside was actually measure the point where it came out of the block. Now, when it came out of the block, it would have, because it's changed back into the same medium, diverged further away from the normal and parallel with the incident ray, because it's back in air. So the refractive index is the same. So that's what would have happened. But we just measured it to this point here and then said, okay, that means, and then we used trig, actually, just used sine to figure out the actual angle in there. So that allowed us to figure out the theta R, and then we calculated the sine and the sine of each of those, because we're going to need those for Snell's law. So Snell's law, there's a number of ways to state it, but the way that I tend to remember it is n1 sine theta 1 equals n2 sine theta 2. Now, what we want is the refractive index of Perspex, which is n2, given that the refractive index of air is n1. Now, we know from the literature that the refractive index of free space, let me put my data up here, n air, the refractive index of free space is 1.000, to as many decimal places as you want. The refractive index of air is very, very slightly different, but it's certainly still accurate to call it 1.00. And that's more precision than we need because it's more precise. It's 3 significant figures. We've only measured our angles to 2. So that is what we know. N Perspex is what we're trying to find out. And you can certainly look that up in literature and find out easily enough. But what we're trying to do here is calculate it. Now, refractive index doesn't really have units. It's a ratio between things, similarly to the way sine is a ratio. And that means that it actually has, that this is kind of entirely a unitless quality, a unitless calculation. So in this case, what we want to do is rearrange to make n the subject, N2 the subject, because N2, actually let's change our subscripts just so that we're clear. So N air sine theta air equals N perspex. I'm just going to make that P to save me some writing. Sine theta perspex. Now we want N perspex, the refractive index of perspex, to be the subject. So I'm going to divide both sides by all of the other side. No, divide both sides by sine theta p and flip it. So NP equals N air sine theta air over sine theta perspex. Now, in our table above, basically I is air and R is perspex, because this is the incident, this is the refracted, this is air, this is perspex. I should label them, shouldn't I? Air, perspex. Didn't quite leave myself room. Okay, so therefore, basically, but we know that N air is equal to 1.00, and anything multiplied by 1 is just itself. So if we make a graph of sine theta air over sine theta perspex, then we can ignore the N air, or just multiply our answer by 1, but that's going to be completely pointless because it just is going to give us the same answer back. So as with so many of these things, we're going to end up with a linear graph. We've got, and we're graphing the sine of the angles, not the angles themselves. Slightly untidy. I'm cramming it up a little bit because we're working on this screen. We're going to have an angle, a line, and I'll leave the graphing to you to do. But what I've tried to do there is draw a gradient greater than 1, because we know that the refractive index of perspex is greater than 1. So the gradient of our line, the rise over run, should be something greater than 1 if we've done everything correctly. And we'll calculate that m, and that m is just going to immediately give us the value of NP. And I'll leave you to look that up in the literature, and you can work that out. We could certainly work on uncertainties in this, and they're relatively large because we've got plus or minus 1 degree effectively, or plus or minus half a degree, because we made it to 1 degree. So you could actually report your value for the refractive index of perspex with an uncertainty and see whether the literature value fits within that uncertainty, as we've done for some of the earlier pracs.